So this is the 11th lecture for ECE 341 random processes. This lecture we're going to wrap up chapter 13 and conclude all the material for 341 this semester. I think what I'd like to do to start out is actually do an example. And this is an example that will help illustrate some of the ideas behind what we've been studying in chapter 13 on stochastic processes. So let's go ahead and take a look at a stochastic process. So let's designate x of n as, or let x of n be an IID random variable or process with the expected value of xn, that sequence, right, being equal to 0 for all n, and let the variance of xn be equal to some amount, we'll call it sigma squared, that is independent of n. So we'll notice that both the mean and the variance are not functions of n in this particular case. So we've got a sequence of independent, identically distributed random variables xn. N just designates the point in the sequence, so it goes from 0, 1, 2, and so forth. There's zero mean, and they have some fixed variance. Just as a little side note, this idea of when you have variance equal to a constant across all time, that is a condition that is called homoscedastic. So we can go ahead and give that a little bit of terminology here. It's homoscedastic. So if you have a homoscedastic process, it's one that has constant variance across time. You could also have something that would be called heteroscedastic. A heteroscedastic process would have something that has a changing or varying variance as across time. So we're just looking at the particular case here, IID random variables, zero mean and homoscedastic, or variance equal to some sigma squared across all time. Okay, nothing too exciting about this. The underlying distribution could really be anything. We're interested in some summary statistics of a derived random variable, or one that is created from x of n through a basic filtering operation. So this particular example is an example derived from signals, a signal processing type of application, a filtering application. So let's go ahead and let there be a new random variable or a new random process, y of n, right, be equal to 1/2 of x of n, but then we're also going to add in 1/2 of what was the previous value of y. So this is a basic filtering operation. We can do a block diagram kind of representation of this, which I think is helpful in its visualization. So we can take process x of n and we can run it into a multiplier. So we're going to multiply that by a gain factor of 1/2. And we are going to add to that to create our desired sequence y of n. But one of the things that we are going to do with that y of n is we are going to maybe delay it by 1. So if you've had signals from me, we can write that delay block as a z to the -1. If not, just call that memory or call it a delay block. So what comes out here is yn -1, which is one time ago that value of our new sequence yn. And it is going to get multiplied by a factor that's also 1/2. And then that's going to feed back in here. So this is a feedback system, right? We have an input, that's our original sequence, our original stochastic process, x of n. It's getting multiplied and added to a feedback term from the desired sequence, or the output sequence, y of n, something along those lines. So we have a new sequence, y of n, and we'd like to know something about the characteristics and behaviors of that new sequence. So let's go ahead and find, for this particular case, the mean value for yn, that sequence yn. Let's find the variance of yn, right? Let's find something like the covariance of y, n comma 1. So this is looking at the covariance between signal y and y shifted by 1. And then let's also find the correlation coefficient rho, right, between yn and yn plus 1. We can base that on the covariance that we found earlier. It's just normalized by variance calculations. Okay, so we're interested in these summary statistics of this new sequence, this new random or stochastic sequence yn coming out in response to the input sequence or stochastic sequence x of n, something along those lines. Okay, for us to be able to answer this, it's not terribly easy from the direct equation. So if I do something like this, expected value of y of n, and what is y of n? I could say this is the expected value of, and what is I of n? It's 1/2, right? We have 1/2 xn, and then we are adding to that, right? 1/2, so we'd have plus 1/2 y of n minus 1. This is a little bit tricky because that expectation involves x, which is something known, but it also involves y, which we don't know. However, since y of n is equal to 1/2 x of n, right, plus 1/2 y of n minus 1, I also know that y of n minus 1 must follow that same equation. That equation is true for all different values of n. So y of n minus 1 is 1/2 of x n minus 1 plus 1/2, well, just one delay from that, that's going to be y n minus 2. And that y of n minus 2 could be gotten as 1/2 x of n minus 2 plus 1/2 y of n minus 3, and so forth. We could keep doing that. And what this suggests is a form of recursion, right? I have an expression here for y n minus 2. I could plug that into here. That gives me an expression for y n minus 1. That could get plugged into here, right? And we can keep doing those kinds of substitutions on a repeating basis. So what do we get out of this? If I do all those substitutions, I find out that y of n equals 1/2 x of n plus 1/2 times what is y n minus 1? Well, that's a 1/2, right? X of n minus 1 plus 1/2 times x of, or y of n minus 2. But what is that? That is 1/2 x n minus 2 plus and 1/2, and I keep going and doing that forever. And what I can get out of all of this is that I notice that y of n can be written in this sort of recursion way. This expanded way that doesn't involve any y's whatsoever. It's just a sum. And let's do that sum on some variable I. 0 to infinity, we're going to get a 1/2 to the I plus 1 of x of n minus I. So I can write y of n purely in terms of xn and its past values, just by back substituting all of those guys forever. And what do I know about these xn's? We know that these guys are all IID, and that's going to really help us out in trying to find at least some of these quantities that we're trying to determine, some of these summary statistics. So if I go over here to expected value of yn, what is y of n? We have now shown that that is going to be just the expectation of this summation I equaling 0 to infinity, and I have a 1/2 I plus 1 x of n minus I, something like that. Okay, well, an expectation is a linear operator, so an expectation of a sum is going to be the sum of the expectations. So I'm going to get that sum getting pulled out if I want. That's a sum I equaling 0 to infinity. And in this particular case, we have expectation of some scale factor, 1/2 I plus 1. That scale factor can also be pulled outside the expectation, so I'm going to have a 1/2 to the I plus 1, and then I'm going to have my expected value of x n minus I. Well, I had already started this by talking about what is the distribution of that x. So if we go back up to x, right, we know that expected xn equals 0 for all different values of n. That was true for all n. So if I come down here to this expectation in here, I'm going to see that that guy is 0. Regardless of whether it's xn or xn minus I, doesn't really matter. All of those guys have 0 mean. All the x's were 0 mean. So I'm going to be summing up some things times 0. Well, anything times 0 is just 0, and if I add up a bunch of zeros together, this thing all comes out being equal to 0. So it might have seemed like an answer you could have guessed. You might have guessed the 0, but we definitely want to be able to go through the mathematics and be able to prove or show definitively that this output process y of n, right, is also 0 mean, which we've just done. So we can conclude at least that expectation of yn part, right? We have shown now that that is equal to 0. So that's one of the pieces that we've got. How about the variance? What happens to the variability of the output process? And how might that compare to the input process? So we know that the input process, right, if we take a look at that input process, it has a variance equal to sigma squared. That variance equal to sigma squared is reflective of the variability of that input stochastic process. And we know that we're generating y, right, based on x and then some feedback terms. So what is your guess? Do you think the variance of y is more, less, or equal to the variability of x? That one might not be so intuitive, and even if it seems intuitive, we still want to make sure we go through the math. So we're looking now for the variability, the variance of y of n. Because we've already established that yn is a zero mean process, variance is equal to the expectation of yn squared, right? Variance is just a mean adjusted second moment, but the mean here is zero, so it's just that second moment expected yn. I'm going to go back and again, because I don't have at this point any kind of knowledge on the underlying distribution of y, that stochastic process, I'd like to put this in terms of x, which I know is IID. And we had this discussion before that independent identically distributed distributions are certainly simpler than the alternative. So I'd like to get this in terms of that known distribution x. So this is an expected value of yn times yn. But what was y? We knew y could be represented as a summation I equaling 0 to infinity, right, of a 1/2 to the I plus 1 x of n minus I. That's the first yn, and I'm going to make the second yn also in the same form, but because they're getting multiplied together and I don't want to confuse the variables of summation, I'm going to sum this on a different named variable. I'm going to do this j equals 0 to infinity, right? And I'm going to have a 1/2 to the j plus 1 x of n minus j, something along those lines. And so this, both are representations. It doesn't really matter what I call the sum variable. I'm just picking the second case to have a different sum variable name so we don't end up confusing them. Okay, so if I expand that through, I have the expected value of some big sum times another big sum, which could be represented as a double nested sum. So this could be represented in terms of what? This is in terms of an expectation of a summation I equaling 0 to infinity, and I could have a summation j equaling 0 to infinity, double nested sum. They both have a 1/2 raised to something, and so I'm going to get a 1/2 to the, well, I plus j plus 2. I just add those exponents. When I take two exponent to power type terms like this and I multiply them together like bases, the exponents add. And then I would have what? I would have my x of n minus I times my x of n minus j, something like that. Expectation, being a linear operator, gives us this basic idea that the expectation of a sum is the sum of the expectations. And we are taking an expectation with regard to that random variable x. So if I take a look at it, the expectation here, if I wanted to do that here, right, this expectation is going to pass those sums. Its expectation is a linear operator, and it's going to pass that scale factor 1/2 to the I plus j plus 2 as well. That's not part of that expectation operator. So if I go ahead and do that, I'm going to get expectation going on the inside, and that means that what I'm left on the outside is I have this summation I equaling 0 to infinity. I have a summation j equaling 0 to infinity. I have a 1/2 to the I plus j plus 2, and then I have an expected value of x n minus I, x of n minus j, something along those lines. Okay, well, what do I do about that interior expectation, expected value of x n minus I and x n minus j? One of the things I might notice is that if I does not equal to j, right, then we're talking expected value x of n minus something, x of n minus something else, and so they are shifted from one another. But these guys were independent, identically distributed. So if there's a shift at all, I can write that expectation of that product because of the independence as the product of expectations. So if I is not equal to j, that expected value of x n minus I, x n minus j is going to be equal to expected x n minus I expected x of n minus j. I get that because the independence, the expected value of the product is going to be the product of the expectations because of the independence that I had on that. Well, what is this first one? This first one is 0, right? And this second one is 0. Those are both zero mean processes, so I get only 0 out of all of those kinds of terms. So how often does that happen? How often does the value I not equal to j? Almost everything in there. If I kind of did a graphical depiction of this sum, right? We are looking over some variable I and some variable j. I'm starting out I going 0, 1, 2, 3, and going out to infinity. And j is the same thing, 0, 1, 2, 3 out to infinity, right? And we are getting terms that correspond to all of these kind of intersection points. And I just looked at all the cases when I is not equal to j. I'm going to highlight the I equaling j parts. That's this line, right? The I not equaling to j is all of that stuff and all of that stuff. So all of those guys, right? If I look at it, that's the I not equaling to j. And if I look at just the kind of main diagonal there, there's I equaling j. So I had a double sum. That's kind of like a two-dimensional part, 0 to infinity, 0 to infinity. It covers a quarter plane. But if I look at the cases I not equaling to j, that gets rid of almost all of it. I'm only left with that main diagonal, which is like a single sum. It's like a single sum, I going from 0 to infinity, right? All the extra terms, only one value for the interior sum survives, and we're left with that one value matching out with the outside sum. So what we end up getting in this particular case, right? We only since almost all of these terms go to 0, since all I not equal to j terms are 0, right? Are 0. Only the I equaling j terms survive, which we write with a single sum, because it's I equaling j. All right, so if I wanted to go ahead and continue this, then we were working on variance of y of n, right? And that's going to be equal to now just those terms that are left, those cases when I going from 0 to infinity, only the j equaling I terms survive, so only one term out of all the interior terms. And so we are going to get a 1/2 to the, it was I plus j, but j was equal to I, so that's going to be I plus 2. That's 2 to the I plus 1, right? And then we're going to have the expected value of, well, when I is equal to j, I'm going to get x of n minus I squared. Now there we can't split that out into an expectation of a product because it's the same term by itself. That's the second moment, and we know that that is connected to the variance of x because x is a zero mean process. We know that expected value of something squared, right, is equal to the variance for those cases when something is a zero mean process. Okay, so how can I simplify this a bit? I know that this piece here, right, is just the variance of x, which we said was equal to sigma squared, right, something along those lines. This term over here, I could write out as a 1/2 to the 2. That's a 1/4 times a 1/2 to the 2i. Well, I can write that 1/2 to the 2i as a 1/2 squared. That's just 1/4 to the I. So I could write that whole thing as a 1/4 to the I. The 1/4 term out front and the sigma squared are both not functions of the sum variable I, and so I could pull those guys out. So I know that I would get a 1/4 sigma squared summation I equaling 0 to infinity of 1/4 to the I. This is just a geometric sum. You've seen these in this class as well as other classes. We know how to solve that guy. So I'm going to get a 1/4 sigma squared, and then that geometric sum, I'm going to take that 1/4 lower limit 0. That's not a very clear 0, so let's clean that up a little bit. 1/4 to the 0 minus 1/4 to the final limit, that's infinity plus 1, all over 1 minus the ratio, 1 minus a fourth. These are just standard known sums. We've seen them before this semester. So 1/4 to the 0 is 1, 1/4 to the infinity is 0. So I'm going to get 1 over 1 minus a fourth. 1 minus a fourth is 3/4, so I'm going to get 1 over 3/4. That's going to be 4/3. So I get a 1/4 sigma squared, right? 1 over 3/4, which is 1/4 sigma squared 4/3. The 4's cancel, and I'm left with sigma squared over 3. So indeed, we do see that the variance of y, our output process, does depend directly on the variance of our input process, and it's one that has gotten smaller, right? We've reduced our variability. The output sequence has a lower variability than the input sequence. Variance of yn, right, is equal to the variance of xn divided by 3. Now, I suspect some of you maybe did make the guess, maybe have, I don't know, made the guess that the variability of y was going to be less than x. I think it would have been much less likely that you would have guessed correctly that it was exactly 1/3 of the variability of x. And so definitely needed to go through the calculation and processes. So now we're going to go to the third thing that was asked for, and that's the covariance of y, right? So we were looking for covariance of y. This is autocovariance as a function of that index n, and then a delay or an advance of 1. So one of my output variables, y of n, and then one shifted one away from that, y of n plus 1. So this guy is just the covariance, right, of, we're going to have y of n and y of n plus 1. That's just definitional. So we had talked about the definition of covariance for sequences before. Okay. Well, what is that going to be equal to? Covariance is a mean adjusted second moment. So this is the expectation, right, of, and we are going to have yn minus mu. Oh, but those guys were 0. We'd already computed that. So since yn is also 0 mean, we're just going to get an expectation of yn times yn plus 1, something along those lines. And I'm going to write this out slightly differently. I'm going to just expand what I know is that yn plus 1 term. So this is expected value yn. What is yn plus 1? I know that that is a 1/2 of xn plus 1, right, plus yn. So that was just from the original recursion formula. So I've got an expectation of a product here, okay? So if I build that out a little bit, that's going to be equal to an expected value of 1/2, right? I'm going to have 1/2, and I'm going to have yn xn plus 1, right? And I'm also going to have in here a plus 1/2 yn squared. Expectation of a sum is the sum of the expectations. Let's take the second part of that expectation first. Expected value of a 1/2 yn squared. The half gets pulled out, so I'm left with a 1/2, right? And then it's expected value yn squared. Because y is a 0 mean process, expected yn squared is just its variance. We just computed that. We knew that that was sigma squared over 3. So I'm going to get a 1/2 times sigma squared over 3, right? That is from this kind of second term. Whoops, let's close that down, put back on my pen. So that guy came from this. How about this guy? What does that guy give me? Now I'm talking the expected value of 1/2 yn xn plus 1. So I can pull the half out. I'm going to have a half, and I'm going to have the expectation of yn, and I'm going to have x of n plus 1, something like that. So I need to be able to do something on that. We know, since, I'm going to do a little logical argument here, since y of n only, right, depends on our x1 or xn, xn minus 1, xn minus 2, and so forth, right? It is independent. It must be independent because that sequence of x's is all independent. It must be independent of xn plus 1. Xn plus 1 hasn't come in yet. And so it's not made up that value of of the output sequence or y of n. So y of n is independent of that future input x of n plus 1. And because they are independent, we know that that expectation will just be the product of the expectations, right? So the expectation in that case of yn xn plus 1 will equal expected yn times expected xn plus 1, and we know those guys are both 0, right? So this guy's 0, that guy's 0. We're going to get this whole thing being equal to 0, and I'm left with the final result that I was looking for. I was looking for the covariance of my output y, right? N by 1. So a shift of 1, it's an autocovariance. A shift of 1, how it's kind of a measure of relationship between of yn and yn plus 1. And what we see on that is that we don't have 0 like we would for the independent identically distributed sequence x. It has a value 0 for this. This one's sigma squared over 6. So less variability, but still something that is non-zero, something along those lines. So, and we know that is what? We know that that is the covariance of y of n plus 1, something along those lines. So that was one of the other ones that was asked for in there. So that's a bit about that covariance. So what can I do with that covariance? I can find the correlation coefficient. We had talked about correlation coefficients before. This is the amount of linear dependence, right? So kind of a straight line approximation on that. We know the correlation coefficient should be a value between -1 and 1, something along those lines. And that if it's positive, that means there's a positive correlation, right? If it's negative, there's a negative kind of correlation. And the closer it is to 1, the more it would fall on a straight line. So rho of yn and yn plus 1 is equal to what? It's the covariance of yn with yn plus 1 divided by, right? We need to divide by sigma yn and divide by sigma yn plus 1, something along those lines. We just computed the covariance. That was that sigma squared by 6. And we also had previously computed what is sigma squared of yn and also sigma squared of yn plus 1, because it never changed. Those guys were each is a standard deviation. The square root of sigma squared over 3, but you square them together or you multiply one by the other, we're just going to get a sigma squared by 3 there. You see the sigma squares canceling, and I'm going to have 1/6 over 1/3, which comes out to being a half. So we end up getting here what? Rho yn plus 1, right? If I was going to plot, if I scatter plotted yn against yn plus 1, you would see them having a positive correlation with one another, right? It would not be like perfect straight line correlation, but it would definitely be a positive correlation. The bigger is yn, the bigger is we would expect yn plus 1. And so we've made our calculation on that one as well. So that concludes really what we asked for in this example. It's just a pretty straightforward process where we had what? We had an original IID sequence coming in. That was something that we called x of n. That went into kind of a filtering structure here. And if you've taken signals or done some other kinds of filtering examples, like in the embedded systems class, you might recognize this as an IIR or an infinite impulse response filter. So these are a very common kind of structure. So we feed this random sequence in. It becomes a new output random sequence, and we're kind of curious about the behavior on that. So we found things like its mean, the variance, the covariance, and the correlation coefficient for that output, at least some of the values on that. That's that example. I'm going to switch over to a different part. I'm going to go back to a set of notes that have been pre-recorded or pre-written, because a lot of these are definitional, just to get us through the remainder of the lecture here without spending a huge amount of time. Most of this can be gotten through pretty quickly. So let's go ahead and finish out the chapter in the semester. So some of this is definitional, and some of it's properties that, if you're lucky enough to get them, again, really simplify your life. The first one's a definition. It's the definition of a stationary process. Stationary, as you might expect, means something that isn't moving as a function of time. So a stationary random process is one that's got a PDF that doesn't depend on time. So if I take a look at my probability density function, right, for that stochastic process x of t, if I delay or shift that by some amount tau, we should get no change in that underlying distribution. So we should just have a basic distribution. It doesn't change for different values of time. That's a bit of an oversimplification, actually. If I need stationarity in what is called the strict sense, and so this is a term, strict stationarity, the strongest form of stationarity, strict stationarity, actually requires that the joint distribution, right, across x of t1 all the way through tm is unaffected by any kind of shift. So you could shift it any amount across any number of values x in any size vector. So all these different joint distributions are unaffected by that shift. So it really tells us that there's no impact of time on the underlying distribution or any of the joint distributions associated with that stochastic process. I gave there the probability density function. There's something very, very similar for the joint probability mass function should your stochastic process be a discrete random variable type, right? And so it's the kind of logical extension on that. We just have instead of a time t, we have indexes n, right? And instead of a shift tau, we would shift by some integer amount k. This is all covered in the book as well. They're just analogous forms. These are not obvious equations, so they're not obvious to see, and they're certainly not easy to show in general. These can be very difficult to show. So it can be a major pain to try to go through and show that an underlying stochastic process meets the conditions for strict stationarity. If we are lucky enough to know that it is strictly stationary, either by construction or because we went through that tedious, horrible work to try to show it, we would know some consequences. A stationary process has a mean, right, that doesn't depend on time. So mu x of t is just mu x. It's going to be the same value for all values of t. And that makes sense, right? A stationary process is not supposed to have things change as a function of time. So all these summary statistics, means and correlations and covariance and all that sort of stuff should not have a t in it. So in the same way, our correlation function, rx of t comma tau, is the same as rx at 0 because it doesn't change as a function of time, which we could call just rx of tau. So the correlation can vary as a function of the shift between the signals, but not at the absolute time that they occur, right? So it wouldn't matter that if I looked at a signal starting at x0, at time 0 and shifted it by 1 second, or if I looked at the same process at time 10 and shifted 1 from that. If I have a stationary process, the beginning or the starting time or the absolute time, the t in there doesn't matter, but the shift of one relative to the other would matter. It would matter in there. Covariance is the same sort of way. Covariance usually depends on not only the shift between the two waveforms, but also the absolute time that the waveform is aligned at. If I have a stationary process, we know time doesn't come into play, and so things just depend on the shift, and we can get that as the correlation minus the mean, and the mean, again, doesn't depend on time, so we get a purely time-independent or no dependence on time covariance function on there. So correlation, covariance, mean, all without a t in there. We had already mentioned that strict stationarity is tough to prove or guarantee, but there are easier and still very useful conditions that are related to this idea. Probably the most common one that you see in the literature is something called wide-sense stationary random processes. It gets kind of boring, just like for independent identically distributed, it gets boring to write that all out, so they say IID. Wide-sense stationary processes, it's again kind of boring to write it always out, so they will just abbreviate that WSS, so a wide-sense stationary process. Rather than require us to know all of this stuff about joint distributions, right? All of these joint distributions being not affected by the start time, by the t, and they're basically being t independent. A wide-sense stationary process only really requires us to be looking at a couple of the statistics. It's going to say that the mean is not a function of time, and that the correlation is not a function of time, and as a consequence, the covariance is also not a function of time. The strictly stationary processes would have a whole bunch of other stuff, maybe third order moments or 10th order moments or 1000th order moments or all these other cross terms, and there would also not be a function of time. Here, wide sense stationary just says these first couple, the mean, right, and then the correlation, and as a consequence, the covariance need to not be functions of time. In general, if you have wide sense stationary, that's a good thing, but it does not lead to stationarity. So in general, you cannot say a process is strictly stationary just by knowing that it was wide sense. However, if you knew something was strictly stationary, you could say that it is wide sense stationary. We've seen stuff like this before. We had seen before that just because you have a correlation coefficient equal to 0, for example, does not mean in general that you get independent random variables. But if you have independent random variables, you do get a correlation coefficient equal to 0. It's a very similar kind of logic as we saw with that. Some properties that we get if things are wide sense stationary. All of these are proven in the book, based on our time here. I'm not going to go through the proofs. The proofs aren't terribly exciting to anyway, but some properties of wide sense stationary. We can take a look at that correlation function, right, at 0. So this is what expected value of x squared, basically. That is always going to be greater than 0. It is expected x squared. It is the average power, if you want to think about that. And that is done over ensembles, and it's constant over t because it's stationary, or wide sense stationary. It shouldn't depend on the value t or the time t that we are looking at. Another consequence that we get out of this that's quite interesting is that the correlation function Rx of tau is an even function, so it's equal to its own reflection. And we also find out that the size of the correlation function is always less than or equal to the correlation function at 0, right? And so Rx at 0 gives us the biggest possible value. Remember, Rx of 0 is expected value of x squared. Now, if I start shifting x relative to itself, right, any shift value away from them lining up perfectly ends up giving us a smaller correlation value. All the proofs are given in the book there. There's another term, so this is definitional again, the definitional term for the term ergodicity. Ergodicity is just a stationary process where time averages approach ensemble averages. Again, probably with the amount of time we have here, we're not going to dwell on this. It is a nice property to have because if I have an ergodic process, we can replace ensemble averages with time averages. Okay, so we could take those ensemble averages and replace them with time averages. Why is this kind of a neat property or a desirable property? Part of the reason is that it's oftentimes pretty cheap to get samples or values of a random process across time, but it can be very, very expensive or difficult, if not impossible, to collect multiple ensembles. You might have some random process associated with a very expensive experiment, right? You run that experiment once and you get a whole bunch of time data. You might not be so easily able to repeat that experiment just because of the cost involved, or maybe the conditions change. And so getting the ensembles of that, restarting that random process again with identical starting conditions would be almost impossible or certainly expensive. If it was an ergodic process, we wouldn't really care so much because all the stuff that we might have gotten by averaging over ensembles can be gotten by averaging over time averages. So ergodicity would be a really desirable process property. We had talked about correlation and covariance, both in the auto sense. So we talked autocovariance and autocorrelation. So that was expectation of a signal with itself and allowing some shift between those two signals. There's also the idea of cross correlation. Just like the correlation before or covariance before are oftentimes very useful, cross correlation is also a highly useful one. In fact, when I made the statement before that we use correlators a lot to do things like radio astronomy or GPS or taking a look at doing like mapping for underground features like doing oil exploration. All of these kind of correlators are probably more accurately doing forms of cross correlation. It's very similar to what we saw for correlation. It's just instead of a signal X with itself, we're doing x with another signal, and that other signal can shift relative to x. So our definition for cross correlation, we're going to call that R sub xy. We'd seen something similar to this before when we had talked pairs of random variables or random vectors. It's just the expectation of x and y, but we allow y to be shifted in time from x, right? You can also do the discrete version of this. It's a pretty obvious one. So cross correlation, right? It's an expectation of x and y where y is allowed to shift from it. Now, if x and y are what are called jointly wide sense stationary processes, what does that stationarity mean? It means that time should not really be coming into play here. And what does it mean to be jointly wide sense stationary? So a joint wide sense stationary process is one where x and y, either one of them, are wide sense stationary themselves, and that the correlation, the cross correlation function, only depends on the difference between x and y, that tau value or the k value if it was a discrete case. So that says rxy of t comma tau is just rx of tau. It doesn't matter the absolute t, it only depends on the relative shift of y from x, or the same thing for the discrete type case. If we have something that is jointly wide sense stationary, right, we get a simplification in that cross correlation, that you don't have to worry about the t's, and furthermore, you get some of those properties that we'd seen before, like the cross correlation between x and y is equal to the cross correlation's reflection. So you get that evenness in the cross correlation function. We're down to the home stretch, one last topic, and it's a quick one. Gaussian random processes. We looked at bivariate Gaussian, and then we looked at a Gaussian random vector. This is a Gaussian random process. So it's a random process. So x of t, it is something that's going along in time, and we want it to be Gaussian. What conditions have to be satisfied for something to be called a Gaussian random process? Well, x of t is a Gaussian process if and only if we can create a vector x that's created out of x1 through x of t1 and through x of tk, right? If that vector is a Gaussian random vector for all possible values of k and all corresponding times out of those vectors, then we have something that is a Gaussian random process. So again, this could be a little bit of a challenge to show. However, if we're lucky, and there's certainly cases that justify this, if x of t is what is called wide sense stationary Gaussian, then we certainly get some help. Not only that, if something is wide sense stationary Gaussian, in other words, if we show that the mean does not depend on time, right, and things like the correlation do not depend on time, then we can also conclude that x of t is a strictly stationary Gaussian. We get that most strongest form of stationarity. You rarely get the case where wide sense stationary leads to strict stationarity. If you go back to when we were talking about some of these concepts in here, we had looked at the case and we had said that basically wide sense stationary, right, does not generally imply stationarity, but stationary does go to wide sense stationary. In the case of Gaussian, it turns out that if we have something that is wide sense stationary, it does lead to strictly stationary, unusual. This might not be hugely surprising, though, if you go back to like the bivariate Gaussian that we looked at before. In the bivariate Gaussian case, we noted that when the correlation coefficient was equal to 0 for a bivariate Gaussian, it ended up giving us independence. So we have seen this kind of quirky behavior from a Gaussian before, where uncorrelated gave us independent. Here we're getting something where a weak form of stationarity, wide sense stationary, gives us the strong form, the strict stationarity. There is also something called a white Gaussian process. White Gaussian processes are also highly desirable. A white Gaussian process, W of t, is really a stationary Gaussian process that is zero mean, okay? And its correlation function is basically a delta function. What does that mean? That means that if you look at the expectation of that process with itself with no shift, right, you can get some value. That's like the variance of the process. But if you shift it all, that correlation function goes to 0, and because it's zero mean, that also means the covariance is 0, and that also means that the correlation coefficient is 0. And what that really gives us, because the correlation is 0, and because Gaussians are goofy this way, when correlation is 0, it also gives us independent. We end up getting something that is independent for any amount of shift, any value tau. These are spectrally rich functions, and it's one where if I take a look at the expected value of w squared, right, because that looks like a delta function, and direct delta functions, we did introduce these before, they have an amplitude that actually goes off to infinity. So we know expected w squared is rw of 0, and that's going to go to infinity because of that delta. It's not a physically realizable process. You actually can never get something that is truly white Gaussian, but it definitely is highly desirable. All the values from one instance to the next are completely independent from one another, and it actually has some very appealing characteristics for all sorts of applications, including a lot of communications applications. We can get, however, things that are approximately white, or they're at least white over a spectral range. That's something for a different class, probably for a communication class. This gets us through the end of chapter 13, and we're basically done with the semester.